So I think let's start. Um, so uh, so the key thing we have discussed, a couple of key important points we have discussed yesterday is um, that high electron mobility in a transistor is usually made on heterojunction, and we mentioned that heterojunction, uh, to create heterojunction we need two dissimilar materials, but the key aspect is those dissimilar materials should have a good lattice match. Okay, and we did mention that gallium arsenide and aluminum gallium arsenide has a very good lattice match for different values of x from 0 to 1. It has a very good lattice match. Okay, so it can be they can be used to create heterojunction. Other there are many I mean there are many materials which we can integrate or can use to create heterojunction. Um, for example, we can create heterojunction using gallium arsenide and indium arsenide. Okay, I forgot to mention this particular point yesterday. Okay, indium arsenide and gallium arsenide. The reason I am mentioning this will be clear just now. So, and this is lattice constant. Okay, so gallium arsenide has lattice constant around 5.65 angstrom. Okay, whereas indium arsenide has lattice constant around 6.08 angstrom. So they have a quite poor lattice match. So what people usually do, uh, they create this heterojunction on the indium phosphide. Okay, indium phosphide has uh, sorry, indium phosphide has uh, lattice constant around 5.88 angstrom, and it is found that this lattice constant of this heterojunction comes around x equal to 0.47. Okay, so for creating um, gallium indium arsenide. Okay, um, I mean you will see in the books it is like it is written like this, because we usually use this particular x value, and um, we deposit this material on top of indium phosphide to get good lattice match and so on. Okay, and now anyway, so lattice matching is a very important criteria um, for heterojunction formation. Okay, uh, another important point we have discussed is in case of heterojunction formation, there can be notch maybe at in the conduction band or valence band, depending on the materials we are using. Okay, but the thing is because of the notch there will be band bending. You remember we have drawn something like this. Okay, yesterday, and you see this was our aluminum gallium arsenide side, and this was our gallium arsenide side, and we did say that this delta EC down here, this band bending has to be delta EC, so that at thermal equilibrium there will be no further electron transfer, and this because of this additional band bending. Okay, the built-in potential is more than that of the built-in potential we get in the homojunction case. Okay, and you remember we wrote it as Vt ln NAND by Ni square plus delta EC over Q, right? And because of this additional band bending, there will be the concentration in this notch here will be more, because the concentration of carrier is, it is possible to show that it is proportional to exponential delta EC plus VBI over Vt. Okay, so this is basically your VBI, that is the built-in potential of the heterojunction, and because of the additional band bending there will be extra electron in the notch. So this part we have discussed in the last class yesterday. So let's now quickly go through the working principle of HEMT, or how this device works basically. So you remember we have drawn the schematic of HEMT structure yesterday. So it had a semi-insulating gallium arsenide layer, which is basically doesn't have any role um, in the device, the current carrying so this part of the material basically used for give mechanical support. So there is here very lowly doped or undoped gallium arsenide. Okay, and in this undoped gallium arsenide there will be notch, right? So this there will be notch here, and we will create N plus or N plus plus region in aluminium gallium arsenide. Okay, so this is heavily doped or highly doped aluminium gallium arsenide. Okay, and so this is my source, this is my drain, and this area is basically your gate. So this is the notch area through which the electron will flow. Okay, so this is the notch area, or you can say this is the channel. It is of course on the gallium arsenide side, but at gallium arsenide aluminum gallium arsenide interface. Okay, I also mentioned yesterday this contact is ohmic contact. Okay, both say source and drain contact, but here this contact is rectifying contact. Okay, this contact is rectifying contact. Now you see, to explain the working principle, you see it is like a MOSFET and MESFET. What is MESFET? MESFET is metal semiconductor field effect transistor. Metal semiconductor field effect transistor, that is MESFET. So when you MESFET, often we create using gallium arsenide. So if you try to make gallium arsenide based FET device, gallium arsenide doesn't have good oxide layer. So there will be basically no oxide. So in gallium arsenide based FET, we'll have gate directly deposited on top of gallium arsenide. Same here, there is no oxide layer. The gate the gate metal is directly deposited on top of aluminum gallium arsenide. Okay, but we have to make sure this contact is Schottky contact or rectifying contact, and also these contacts here we will use a different contact so that they will act as a ohmic contact. Okay, now the thing is, so it's kind of a MESFET because there is no oxide or insulating layer as such. Okay, so it is metal semiconductor field effect transistor. Why it is field effect we will discuss in a minute. But what about MOSFET? As I said, this is a combination of MOSFET and MESFET. Why it is MOSFET? This is MOSFET because the current is not flowing through this aluminum gallium arsenide layer. Although there is a provision that current can flow because this aluminum gallium arsenide layer is just a piece of semiconductor, and current, if you apply bias between source and drain, current should be able to flow in this aluminum gallium arsenide layer. But we have to prevent this. Okay, how we can prevent it? So we can prevent it by depleting this entire portion. So if I deplete this entire portion, then the current can't, or the carrier can't flow between source and drain through aluminum gallium arsenide. The carrier can only flow through this channel. Okay, through this channel. So if we manage to deplete this entire portion, then you see it acts as a MOSFET kind of structure. So this portion is then depleted. Okay, this entire portion is then depleted. It is then acts as a as kind of a MOSFET structure. Now this dielectric constant of aluminum gallium arsenide is around 12.8. Okay, whereas you remember the dielectric constant of SiO2 is around 4. It is 3.8 to be precise. Okay, so the dielectric constant of this aluminum gallium arsenide is almost 4 times that of SiO2, right? So you see it is kind of a high K dielectric material compared to SiO2, right? But as there is no current flowing through this aluminum gallium arsenide, we can we can think this structure is similar to that of MOSFET. Okay, and how it is similar to MOSFET? Because there is no, as if there is no insulating layer, and the metal is directly deposited on top of the semiconducting layer. So that is how it is. It is also a MOSFET. Now the thing is how it works. So when this junction is formed, the electron from this highly doped N plus region, okay, will go to this, will travel to this gallium arsenide, undoped gallium arsenide side, and they will basically accumulate in this notch layer, okay, notch portion. Now if we bias this gate, we have to bias this gate so that we can deplete this aluminum gallium arsenide. If we don't deplete, as I said, there will be current through this aluminum gallium arsenide layer, and the mobility of those carrier will be low because it is highly doped. You see, okay, there will be lots of ionization scattering. So our goal is to deplete this entire aluminum gallium arsenide portion. So, but how we are going to deplete it? We are going to deplete it by applying bias at the gate. Okay, so this is gallium arsenide, this is aluminum gallium arsenide. Okay, and this is our gate. Now if we apply negative voltage here, okay, if we apply negative voltage, if VGS is negative, then what will happen? Positive immobile ions will be developed here. Okay, so this depletion region is because of the a Schottky junction. Okay, so this depletion region is because of the Schottky junction, right? Now this is N plus or N plus plus region, and this is very lowly doped P region. So there will be additional depletion region which is because of the PN junction. Okay, so right, so there will be additional, of course there is a notch here, okay, at the interface. So you see there are two depletion region in aluminum gallium arsenide side. One is because of the Schottky junction, metal semiconductor junction, and this other one is basically because of the PN plus junction. Okay, so there is depletion region. Now, so as I said, our goal is to deplete this entire aluminum gallium arsenide so that we can force the electrons to move through this notch or through this channel, okay, without allowing them to flow through aluminum gallium arsenide. Now, how we can deplete them? We can deplete them by applying voltage at the gate, right? Now, so if we keep on increasing this voltage, if we keep on increasing this negative voltage, okay, if we keep on increasing this VGS in the negative direction, then what will happen? This depletion region will keep on increasing, depletion width, right? Because it needs then to image the charge, it needs more and more positive charge, okay, right? So more and more depletion width is going to increase, right? No, so as depletion width keeps on increasing, at some point this depletion region, because of the Schottky, will touch or will merge that of the depletion region of the PN junction, right? So understood? So if we keep on increasing this VGS, the depletion region at aluminum gallium arsenide, because of this Schottky junction, will keep on increasing. Okay, because if you increase VGS, there will be more and more negative ions on the metal side that will attract more and more positive immobile ions. Okay, right? So as we keep on increasing this VGS, this depletion region will increase, and at some point it will touch the depletion region of the PN junction, right? PN plus junction. So we can draw a let me draw it once more, and we can draw the electric field, corresponding electric field. So
Sir,
yes,
whether the gallium arsenide layer is undoped or lightly doped.
uh, hardly any difference. You can write lightly doped if you want. Yeah, lightly doped, right? So compared to aluminum gallium arsenide is very lowly doped. Okay. Now the thing is, so when we didn't apply any voltage, say that time the depletion, there will be a depletion region because of this Schottky junction. Okay, so let me draw the uh, so let me draw the electric field. Okay, so there are positive immobile ions here. Okay, and negative immobile ions here, right? And electric field is our convention is electric field is from positive to negative. So electric field this direction, here electric field will be this direction, right? Always positive to negative. So we can, that electric field will be, say, something like this. Okay, in the PN junction. What about electric field here? Electric field here will be something like this. Okay, so this is, say, point number 1. It's a point number 2. Okay, now this portion is when, say this electric field is when there is uh, no applied voltage. Now if we keep apply, if we increase the applied voltage, okay, so these depletion region will expand as I mentioned in the previous slide, and then ultimately if you keep on increasing this applied voltage at the gate, okay, ultimately this depletion region will touch point 2, okay. So then electric field will be something like this, right? So if we increase electric voltage at the or bias at the gate, then at some point both the depletion region will touch each other, right? Now if you then keep on increasing, because what is the purpose of the gate? Gate needs to deplete, okay, so that we prevent the flow of carrier through aluminum gallium arsenide. Also gate need to control the amount of electron in the notch, because otherwise how we will because otherwise there will be no variation in the current, right, through the notch. So in MOSFET what we do, we apply gate voltage, and depending on the amount of the gate voltage, the channel electron will change, amount of electron in the channel will change. This is exactly what we are trying to do here. We will not only deplete the aluminum gallium arsenide, entire aluminum gallium arsenide, we also then, if you keep on increasing it further, then what will happen, it will reach, so then what will happen, so if you keep on increasing, say this is your, okay, so then this Schottky, I mean the depletion region of the, because of Schottky, will invade in the PN junction depletion region and will take some of the positive immobile ions from those PN plus depletion region. Okay, so those PN plus depletion region is now belongs to Schottky PN junction, Schottky metal N plus junction. Okay, so that will then reduce, I mean that will, you see now the electric field is like this here, okay, so that will now reduce the PN junction depletion region, okay. In other words, now the notch, inside the notch, and if this depletion region reduces, you see band bending will also reduce, okay. So the depletion width basically signifies the band bending, right? The depletion will be as far as there will be band bending, so the band bending will reduce because this depletion width is reducing, okay. In other words, if we manage to change this band bending through gate, we will be able to control the amount of electron, because as I said, the amount of electron, um, okay, exponentially related to delta EC over VT, okay, along with VBI. So this delta EC, if we manage to reduce that band bending, this delta EC is coming because of the notch and this additional band bending. So if we manage to bring this band bending back to their close to this homojunction portion, then the amount of electron will get reduced, okay. In other words, we can control the amount of electron from gate side by applying bias voltage, okay. The more and more negative voltage we will use, at some point the depletion region from both sides will not only merge in the Schottky depletion region required for the Schottky junction, okay, will invade inside the PN plus junction, PN plus depletion region, and take some of the immobile ions from the PN plus depletion region, right? That in turn, what that will do, that will reduce the depletion region on the gallium arsenide side, or we can also say, so that in turn reduces the band bending, okay. So that will in effect reduce the amount of electron in the notch. So that is how we can control the current through the, so in the, how we are getting the current. So if we apply bias between source and drain, okay, if we apply bias between source and drain, then the current will flow basically, I mean the electron will flow from source to drain and current will flow from drain to source, but the amount of current obviously depends on a number of electron present in the notch, and this number of electron we can control by applying proper gate voltage, I mean proper bias voltage from the gate side, right? Now the thing is, uh, so I mean, let me, so what we, so there are different parameters. One of the parameter is VGS deplete. Okay, so that is the gate source voltage which is required to deplete the entire aluminum gallium arsenide. Okay, and this VGS and what is V off? V off, or basically the V threshold. Okay, you can, here we usually call it V off, and V off is basically VGS deplete. Okay, VGS deplete minus delta EC by Q. Okay, so the concept is, so this is when we are not applying any voltage. Okay, this is when we are not applying any voltage, and when we are applying a voltage and pushing the band bending back to delta EC. Okay, so that it is in the homojunction, aligned to homojunction, that time we call it as V off. Okay, so V off, for finding V off, it is basically VGS deplete plus additional voltage we have to apply from the gate side to reduce the band bending by delta EC by Q. Is that clear? So the conceptually what we, or the way we define V off is VGS deplete, that is we have to apply to deplete the entire aluminum gallium arsenide. On top of that, we have to apply additional voltage, that is delta EC by Q, to, because you see VGS deplete is negative in this particular case. So this plus additional delta EC by Q we have to apply, so that we reduce that band bending. Okay, in such a way so that it becomes same as that of the homojunction of gallium arsenide, this particular conduction band region. And then we call it, there is very minimum number of carrier in the in this notch, right? And the way we I'm not going into that direction, the way we define VGS deplete is basically VBI, that is the built-in potential. You know, built-in potential VBI is VT ln NAND by NI square plus delta EC by Q, that is VBI. Okay, VBI plus VBI minus VPO. Okay, so VPO is basically pinch off voltage of MESFET. Again, what is pinch off voltage of MESFET? I just don't want to go into that. Just give me a second. Hello. না আমি একটু ক্লাস নিচ্ছি, হ্যাঁ পরে কথা বলবো। Sorry. So this V off is VBI minus VPO. Okay, VGS deplete is VBI minus VPO, and VPO is basically pinch off voltage of MESFET. Okay, and this VPO, it is possible to show this VPO is QND A square over 2 epsilon R epsilon naught. I mean, you don't have to remember this, just for the sake of discussion I am mentioning this particular expression. If you want, you can memorize this, but this, what is this A is basically the thickness of the aluminum gallium arsenide layer. A is basically the thickness of the N plus layer, right? Now the thing is, this A has to be as small as possible. Why A has to be as small as possible? if in case of MOSFET, you remember, in case of MOSFET, the channel in the channel charge, Q channel can be written as VGS minus VTH. Okay, and in case of HEMT, similarly we can write Q channel is equal to CS VGS minus V off, because V off is like the, as I mentioned, V off is the threshold voltage of the HEMT, and this CS here is epsilon R epsilon naught by A. Okay, so the lower the A is, the higher will be the capacitance. Okay, so the lower the A is the thickness of the aluminum gallium arsenide in this case. Okay, so the lower the A, the higher will be CS. Now the thing is, one additional point I would like to mention here, this aluminum gallium arsenide side will have a special layer, and this special layer is made of undoped gas. Okay, undoped gas. Maybe I haven't drawn it today. I have drawn it in the last class yesterday. So there is a special layer here. Special layer here. Okay, this special layer is undoped aluminum gallium arsenide. Okay, and why this special layer is required? This special layer is required because then the immobile ions present here, okay, will have less influence on the electron passing through this notch, because the concentration of immobile ions on the aluminum gallium arsenide side is very high, you see, whereas in the concentration of the concentration of the immobile ions here is much lower, right? So we are that is why we use undoped or very lowly doped gallium arsenide, so that the electrons passing through this channel or this notch will encounter or will interact this immobile ions. So this interaction is very less, because the concentration of immobile ions here is very less, because it is undoped or very lowly doped, whereas this is very heavily doped aluminum gallium arsenide. So there is lots of immobile, or the concentration of immobile ions near this notch is very high. So what we can do to avoid this or reduce this interaction, we use a special layer. Okay, if this special layer is thick, then we will have very small interaction between these positive immobile ions and those electrons in the notch. But if you increase this thickness of this special layer, which is basically undoped of aluminum gallium arsenide, then this increase in thickness will increase the value of A. And as I said, we don't want very large value of A, because then the capacitor will decrease. Okay, value of capacitor will decrease. So it is a like so it has both plus and minus. You have to use a special layer, okay, so that so because here this quantum well or this notch we will discuss later on when we will discuss the quantum effect of nanostructure. We will see that in this notch there will be discrete energy levels, and these discrete energy levels will have electron, and those electrons have like wave nature. So these waves will go beyond this notch. Okay, so these electrons, in other words, these electrons can interact with the immobile ions present here. Okay, present here and here, but we are not bothered about immobile ions present in the gallium arsenide side, because that is anyway concentration is very low. But these immobile ions present here near in the aluminum gallium arsenide side is of concern. So how we can check that? We use very lowly doped or undoped aluminum gallium arsenide here to reduce that interaction. Okay, but the thickness, if we have like larger or thicker aluminum gallium arsenide undoped layer, then this interaction will be lower. If it is large thicker, then that will reduce the capacitance value. Okay, so we have to take something in between so that we can manage both of these. Okay, so now the thing is, it is possible to show that that the current the voltage relation is similar to that of MOSFET in HEMT. So if I plot IDS versus VDS, we will have like uh, similar characteristic like that of MOSFET. Okay, here also IDS is equal to mu n CS W over 2L VGS minus V of whole square. Okay, same as MOSFET, similar, right? VGS minus V of whole square, and the corresponding GM, you know GM, sorry, CS W over L VGS minus V of. Okay, so this GM, that is the transconductance, you see GM will be higher in this case. Why GM will be higher compared to that of MOSFET? Why GM will be higher? You see mu n is larger, compared to silicon based MOSFET, because mu n, we mentioned yesterday, mu n at room temperature around 8,500 centimeter square per volt second. Okay, so mu n is high, maybe 8 times, even 9-10 times, so 8 times, let's put it this way, 8 times. Okay, and what about CS of HEMT again is larger than that of C oxide of MOSFET. Okay, if we maintain all the dimensions same. Okay, because here, why I am saying it will be larger, because here epsilon r is of the order of around 12 point something, say 12.3 or 12.4, and it is epsilon r here around 3.8. Okay, so you see it is almost 4 times, or almost 3 to 4 times. Okay, so if it is 3 to 4 times, okay, 3 times, right? So it is 3 times. So if it is 3 times, and here if it is like 8 times, so you see your GM there is almost 3 into 8, 24 times compared to that of silicon based MOSFET, right? This is 3 times, and mu n is 8 times, say. Okay, so almost 24 times compared to that of ordinary silicon based MOSFET. And the cutoff frequency, you know, cutoff frequency is GM over CS, right? GM over C. So this C is different. So GM over C. So you see, cutoff frequency you can achieve from this will be much more compared to that of conventional MOSFET, right? Um, Now you can achieve such HEMT. You can use such HEMT in the enhancement mode or in depletion mode. Okay, depending on whether your V off is in the negative side or V off is in the positive side. Okay, so this, so if you plot IDS over VGS, okay, so this can be, it is possible to so it is it is possible to achieve enhancement type of MOSFET, or enhancement type of HEMT, or depletion type of HEMT, depending on depletion type, and this is enhancement type, depending on how your V off is. Okay, so as I said, your V off is VGS deplete minus delta EC. You remember V off is VGS deplete minus delta EC over Q. So if this is VGS is negative, then you will get depletion type of MOSFET, depletion type of HEMT. Okay. Now this VGS deplete, if you start making it positive, at some point this aluminum gallium arsenide will open up. Okay. So you have to be careful. If you develop a enhancement type of HEMT, you have to be careful that your it shouldn't open up that that aluminum gallium arsenide portion. If it does, then it will it will deteriorate the performance, because then the carrier will flow through the aluminum gallium arsenide instead of through the notch. Okay. What else? Did I miss anything? I think I have covered more or less what I need to cover. One more thing I would like to mention is this. We said in the yesterday's class, in case of aluminum gallium arsenide based HEMT structure, this X is, so X is around 0.3. We usually don't use X more than 0.3, we don't use. Okay. Why we don't use more than 0.3? Because if you use very large value of X, that is, then what will happen, there will be defects in the structure, because so that's number one, because then we will replace lot more gallium with aluminium, and aluminium is the foreign material in gallium arsenide, right? So that will create defects. So that's one point. Second point is, you see aluminum arsenide is a much higher band gap compared to that of aluminum gallium arsenide. So more, or gallium arsenide, because gallium arsenide has Eg around 1.43, right, electron volt, that we saw yesterday. Whereas for aluminum arsenide, the Eg is 2.17 electron volt, right? So if you keep on increasing the and increasing the aluminum content, the band gap will increase. So then it will be difficult to achieve ohmic contact. Okay, because you need ohmic contact at source and drain, right? So usually we don't go beyond 0.4, 0.3, 0.4, okay, of aluminum proportion in gallium arsenide, so that the defects remain minimum, and we can achieve ohmic contact in ohmic contact at the source and drain portion. What else? Uh, So if we reduce the reduce the operating temperature of the device, you see, then the mobility will increase even further. Okay, mobility will increase even further, because you see, we discussed in the last class that here mobility mainly dominated by the lattice vibration. Okay, and lattice vibration increases as we increase temperature. So you remember we discussed that mobility versus temperature in yesterday, and we said that one component where mobility decreases with lattice vibration. So this mobility is because of lattice vibration, and this is the dominant mobility factor in case of HEMT, because there is less interaction between the carrier and the immobile ions. Now this lattice vibration, if you increase the temperature, lattice vibration will increase, and that will reduce the mobility. So if we reduce the temperature, the mobility will increase. Okay, so in fact we can get mobility maybe of the order of reported result is, we can get mobility of the order of 1 lakh, okay, with such devices at 77 K, right? So if you reduce the temperature quite a lot, you can increase the mobility quite high from this. You can get very much higher mobility from this device. Okay, so what that will do, that will basically increase the current. Okay, so you can have larger current, right? Because current has this mobility factor, so increasing mobility will give you larger current. So you see, if we increase the so this is for high temperature or room temperature maybe, okay, uh, and this dotted line is for low temperature. So if you reduce the temperature, your current is going to increase because your mobility increases. So this is I think that's all I would like to discuss as far as the HEMT is concerned. I have uploaded the note already yesterday. Um so you can go through the note. Now in the next class we will discuss HBT, that is high heterojunction bipolar transistor. um, I hope you have submitted um, the assignment I have given to you. Now one more thing is we have to take test, right? So when will be the right time to give test? I personally like to cover more to take the test. So what is the when is the time for taking test? Do you know?